So our vocabulary words today are atom, element, compound, substance, periodic table of elements, and matter. So our first word is atom. It is the smallest particle of an element maintaining the chemical identity of that element. So basically it's one tiny, like microscopic little piece of an element, and it has all of those same properties. If you break down the atom even smaller, then at that point you can't tell that it's still that element. So if you have one atom of gold, it's going to look and feel and have the same density. It'll be just the same as every other atom of gold anywhere. But if you break down that gold atom, then you're just going to have protons and electrons, and you're not going to be able to tell that it's gold anymore. It will just look like generic parts of an atom. So here is what's called a Bohr model. It's basically just a representation or a model of what an atom might look like. We honestly don't know this is exactly what it looks like. This is how we draw it so that it kind of makes more sense to us. So an element is a pure substance composed of the same type of atom throughout. So if it is an element, it only has one type of atom. So if you have an element of hydrogen, it has only hydrogen atoms. If you have mercury, it only has mercury atoms. So it's just one type of atom. All elements are on the periodic table. So if it is not listed on the periodic table, it means it is not an element. So like water or carbon dioxide, those things are not listed on the periodic table. And they are represented by a chemical symbol. So here for hydrogen, the chemical symbol is H. For oxygen, it's O. And for like gold, it is AU. So some of the symbols have one letter, and it'll be capital, always a capital H. And some elements have a two-letter abbreviation or symbol, and then it will be an uppercase letter and then a lowercase. So for like gold, it is capital A, lowercase u. Gold, if this was pure gold, it would only have gold atoms throughout it. It would be nothing else besides just gold. Okay, so here's another kind of way of looking at it. It's the same definition as before, but here we have a bunch of purple balls to kind of illustrate the different atoms. And if you notice, all of these are the same shape, same size, same color. So this substance only has one type of element in it. So we're going to look at a couple examples of elements. So this first one obviously is gold, and again its abbreviation is capital A, lowercase u. Some of the symbols that don't really match the letters, like there's no A in gold, there's no U in gold, they normally come from Greek or Latin roots, because in ancient times people could just dig gold out of the ground, or they could find it in caves, and so they gave gold a name in Greek or Latin. So that's where some of these abbreviations come from. Chemical symbols come from. Our next one is helium. So the stuff you put in balloons to make it float, that is an element. And here, helium also has a two-letter chemical symbol, which is He, capital H, lowercase e. So if you think about it, helium is a gas, and people in ancient times didn't think that gases existed. They didn't know what they were because you can't see them. And so helium and other gases were discovered much more recently, so they have more straightforward chemical symbols because they're based on English. So since this is helium and it was discovered, not that long ago, its chemical symbol is He. So our next example is iron. This is a magnetic metal, and its chemical symbol is Fe. Mercury is that kind of cool liquid metal, but if you touch it too much or if you eat it, you can get poisoned. And its abbreviation is capital H, lowercase g. Is something that's called a metalloid, which we will talk about in a couple of days. And again, it was discovered fairly recently, so its chemical symbol is Si. And this is something that's very important to technology and electronics. So almost every cell phone or computer or tablet, almost any sort of like technology device has a little tiny bit of silicon inside. So this is sulfur. Its chemical symbol is a capital S. It's always yellow and it stinks. Right? A lot of people will say that it smells like rotting eggs, and it is a very noticeable smell. Like when you smell it, it's obvious that it's sulfur. So our next word is compound. It's a pure substance made of two or more kinds of atoms bound together. So if you see over here on the water, it has two different kinds of atoms. It has O, which is oxygen, and then it has H, which is hydrogen. The key point of this is that they are bound together. If we have a mixture, it is also two or more kinds of atoms, but they are not bound. They are just kind of floating around in the same space. For a compound, the oxygen and hydrogen here in water are chemically bonded together, and it's almost impossible to get them apart. So they are hanging on for dear life, and they don't want to let go. So again, here's just another way of kind of looking at water. So the two smaller hydrogen atoms are bound to the larger oxygen atom. So again, here's the same definition. This is an example of carbon dioxide. It has a uniform composition of carbon dioxide molecules. So if you look at this substance or this kind of block of stuff, it is obviously made of two different types of atoms because we have the red and the black. But this chunk of whatever this is, carbon dioxide, has nothing but carbon dioxide molecules in there. So if you see every single molecule in there, which is just what we call the atoms when they're bound together, has two red and one black, all of them. So that means it's a uniform composition, which means it's the same stuff all the way throughout. Compounds also. So by far the most common compound, which people know most about, and probably the most important compound for living things is water, H2O. So something I think is interesting about compounds is that they can have different properties than the stuff that goes into them. So for example, hydrogen by itself is a gas at room temperature, so it's a gas, and it's very flammable, which means it can catch on fire. It can actually even explode if it gets caught on fire. Oxygen, which is the O, also by itself is a gas at room temperature, and it is also very flammable, so it can also catch on fire or explode. When these two combine in the right combination, two hydrogen atoms and one oxygen atom, it is now a liquid at room temperature, and it puts out fires. So the properties of the compound can be completely different than the ingredients of what goes into it. So another example of a compound is baking soda. So this has one sodium atom, that's the Na, that's sodium. It has one hydrogen atom, that's the H. It has one carbon atom, which is the C. And it has three oxygen atoms, which is the O. Here's another compound, it's just regular table salt. It has one sodium atom, again that's the Na, and it has one chlorine atom, which is a Cl. Just FYI, in chemistry, if there was ever a capital I, and there is an element that has capital I as its symbol, which is iodine, the capital I would have the bars at the top and bottom, so it's more obvious that it's an I. So salt is another example of the result or the compound having different properties than the ingredients that go in. So sodium, Na, by itself is silver colored. It is a metal. It's a soft metal, you can cut it with a knife, but if it touches water, it can catch on fire or explode. Okay. Chlorine by itself is a gas, which is very, very, very poisonous. Now this chlorine is a little bit different than the chlorine that goes in a pool, because the chlorine that goes in a pool is mixed with other liquids. It's not just pure chlorine, and that's why it's a liquid. Okay. But regular plain chlorine is a gas, which is very poisonous. So when these two combine, we now have sodium chloride, which is table salt, which is delicious and helps us, cook and make our food taste better. So kind of weird. Then the other two things is a mixture. A mixture is not a pure substance, and when two or more substances combine physically but not chemically. So one, this is not a pure substance. So if you look at this example of like trail mix down here, it's not a pure substance because it's not the same ingredients all the way through. Here we have, it looks like Golden Grams and marshmallows and M&Ms and all kinds of different stuff. So it is not the same thing all the way through. There's different things inside of it. And also we have two or more different substances or elements that combine physically, so they're hanging out in the same space, but they are not chemically bonded. So if you look at this trail mix or whatever, if I just wanted the marshmallows, I could reach in and pick them out and it's not a problem. But if you remember from the definition for compound, compounds are almost impossible to separate. So this is the big difference between mixture and compound. Mixture is not bound together. They are not chemically bonded together, and you can separate them. Compounds are chemically bonded together. They're holding hands, like they're hanging on for dear life, and it's almost impossible to separate them. So we're going to do a few more examples of mixtures. So the air around us is a mixture. It's kind of hard for us to see, but it is. There are different gas molecules floating around. So there's carbon dioxide, there's oxygen, there's hydrogen, there's nitrogen, there could be carbon monoxide, and those are all different substances, and they just happen to be sharing the same space. But the oxygen in the air is not connected to the nitrogen, which is not connected to the hydrogen. They're just kind of in the same area. Okay, so granite is something that a lot of people use on their countertops, and it is also a mixture. So it's a bunch of different types of rocks that have kind of been broken down and then squeezed together to make granite. And so if you kind of see, you can see kind of like the different chunks of the different rocks. There's little black specks, there's big pink chunks. Those are all different rocks that are just kind of hanging out in the same space. Mixture, it has different elements like calcium, there's protein in there, there's water, and it's just a bunch of different substances that spend time together. The way you can separate those parts of the milk is to let it spoil. If you've ever let milk sit out for like a day or more, you can see how it starts getting kind of chunky in some areas, and those kind of like rise to the top, and then there's kind of like a watery looking substance at the bottom, and it's because it is water. So as the milk spoils, the different parts in the milk separate out, and so that's how you know it's a mixture. All right, salt water is also a mixture. So again, one of the key things of a mixture is that you can separate it. So if you have a glass of salt water and you boil it or you let it sit outside for a long time and it's hot, the water will evaporate and the salt will be left behind. So again, that's easily able to be separated, which makes it a mixture. Okay, stainless steel is also a mixture. Now this one is not nearly as easy to separate. I wouldn't go trying it. Your mom might get mad if you destroy her, forks and spoons. But it's a mixture of different metals, and they add carbon to it as well to make it harder so that it doesn't get damaged as easily. But it is different elements and substances mixed together and then shaped to form different tools. Okay. So a substance is any form of matter that is uniform throughout and has consistent properties. So it's basically just something, you look at it, it looks the same all the way through. There's no splotches or, extra parts like floating around. And it just has the same properties all the way through. So whatever's at the top of your container is the same as whatever's at the bottom. So here's ketchup, which is a good example of a substance. It's uniform throughout. So at the bottom of the bottle, it's red and tastes like tomatoes. And at the top of the bottle, it is red and tastes like tomatoes. And it's a liquid all the way through. Like it's the same exact stuff everywhere in the bottle. There's nothing else added. So the periodic table of the elements, it is a table in which all the known elements are arranged by properties. So we're not going to go into too much detail about the rows and columns, but they are there for a reason. The elements are listed in a certain order for a reason, and we'll go into that a little bit more in a couple of days. So here's an example of a periodic table. Sometimes you'll see them colored in different ways. So this one's a little bit more complicated. It has a couple extra colors that we're not going to worry about. The two rows at the bottom, they are supposed to go between, if you look towards the bottom in the yellow, between where it says BA and HF. And then on the row below it, it goes between RA and RF. So all of those fit in those two little spaces. And the reason is because at the bottom of the periodic table, there's so many elements that are supposed to go in those rows that it would not fit well on a piece of paper or on a poster, to be honest. So they drop those two rows down and they kind of show you in the middle like 57 to 71. And then, what does that say? 89 to 103. Okay, so that's where those two rows go. Again, the rows and columns do mean something. They're there for a reason. And I don't want you to worry about knowing all of these. Like, it doesn't honestly really matter that much. We're just going to kind of do our best. Now, on some periodic tables you might see, they might end at like 112, where this periodic table goes all the way to 113. If you look from 113 to 118, there are 113, 115, 117, and 118 that have 3-letter chemical symbols. And it's because those elements have not been discovered yet. So anything from element 92 to the end, so starting right after uranium, let's see where that is. So starting with neptunium, number 93, from 93 to 118, those are all made in a lab. So scientists put those together. You can't just go and dig those up out of the ground. They don't exist in real life, like in nature. So all of those elements are made in scientific labs. And 113, 115, 117, and 118 have not been made yet. They have to be made several times to be verified or checked, and those just haven't made the cut yet. So some periodic tables you might see might just leave those out. So some periodic tables might have gaps there. They may have 114 and 116 because those have already been discovered. So sometimes it depends on when the periodic table was printed, what they include and what they leave out. Okay, and that's okay. It just depends on who's making it and what they want to include. Is anything that has mass and takes up space, so that can include elements, compounds, and mixtures. And then if you look at the illustration, it's showing us the 3 phases of matter, which are solid, liquid, and gas. And remember from primary school, they change from one phase to another when you add heat to them. So you have a solid, you add heat to it, it becomes a liquid. You add some more heat, it becomes a gas. You take the heat away from the gas, it becomes a liquid. You take the heat away from the liquid, it becomes a solid. So you should already know that from elementary school. So here's kind of an example of the atoms in the different states of matter. So gas, the atoms are very far apart, has a very low density. In liquid, they're kind of coming together a little bit more and has a medium density. And then for the solid, the atoms are very closely together. It's a little bit harder for them to move around, and it has the highest density of the 3. All right, so for our notes page, an atom is the smallest part of an element that still has the properties of the element. And examples are sodium, chlorine, and hydrogen. Feel free to add some more examples from your periodic table that you think are cool. A molecule is formed when 2 or more atoms are joined together chemically. So a molecule is kind of another word for a compound. And examples are water and salt. A compound is made of only one kind of molecule and is also a pure substance. So examples are water because it has only water molecules in it. And then lastly, a mixture. Unlike a compound, it is made up of different kinds of atoms and molecules. There are at least 2 or more that combine physically but not chemically. So again, they're sharing the same space, but they are not chemically bound together.